Assalamu alaikum, my students. Also here, welcoming you again to our unit of calculus. As you know that we are discussing these days the definite integral, and we have already found its geometrical meaning. We know now if we have a curve f of x, and it is continuous, and x is equal to a, and x is equal to b, or this is my x-axis and this is my y-axis, then we know that by the geometrical meaning of this definite integral, the area that is under this curve and bounded by this coordinate x is equal to a, x is equal to b, and this x-axis is equal to definite integral f of x dx. We have already discussed it, and we have already given its proof also. Now today we have another concept, that is this definite integral as a limit of sum. We are first going to state it, and after that we will give its proof. This statement is just like this. If we have a just plain, this is our x-axis and this is our y-axis, and for example this is my curve f of x, and it is continuous here from x is equal to a and x is equal to b. The definite integral as a limit of sum says if we divide this distance x from this x to this x is equal to b, if we divide it in n equal parts. For example, I will take the portion like this: p1, p2, p3, p4, and if I draw perpendicular to this curve, so on. If I take now the distance of each, or the length of each portion equals to h. For example, the length from this to this, and from this to this, and from this to this is equal to, if I take that equals to h, then the definite integral as a limit of sum says this area under the curve f of x dx, this definite integral, or we can say that area under this curve bounded by this, it is equal to limit as tends to 0 h summation of r is equal to 1 to n f of a plus rh, and this is also equal to, if we write this formula as h summation r is equal to 0 to n minus 1 f of a plus f of a plus, and this is my definite integral as a limit of sum. We have to prove it. So the definite integral as a limit of sum is now that is also equal to this area under this curve, and that area under this curve is equal to this thing. So now we know we have divided this distance from, that is from this x is equal to a and x is equal to b into n equal parts. So from here up to this, it is equal to beta. Now how many parts we have? N, and the distance of each part is h. So this n h is the distance from this x is equal to a to x is equal to b. But we know that the distance from this x is equal to a, this x is equal to a to x is equal to b, that is equal to this whole distance from this origin to this x. What is that? That is b, and we have to, from this whole distance from this distance of 0 to this point, we will exclude the distance that is from this 0 to this x is equal to a, and we will get the distance from x is equal to a, x is equal to b. So we will exclude here this a, we will get this nh is equal to b minus a. So we will now write this statement, and after that we will prove it. Right, just like this layout. F of x be a continuous function in AB, then prove that A to B f of x dx is equal to limit h tends to 0 h summation from r is equal to 1 to n f of this A plus r h is equal to r, this is equal to limit h tends to 0 h summation of r is equal to 0. The summation runs from 0 to this n minus 1 f of A plus r h. So you write down the statement. Now we will go it through. In proof, you're supposed to draw a graph here. Shell origin, and you take this as x-axis, this one y-axis, and you take your curve like this, and take this point as my x is equal to A, and this one you take x is equal to B. Now, what is my next step? I have to if this is my A, B, C and D. After that, I have to divide this distance dd into n equal parts. So I will divide. And this is B1, B2, so on. And this is Bn minus 1. And here, if it is P1, P2, so on, after this will be n minus 1. So I will write this proof here. Divide BD into n equal parts. Divide into n equal parts. Each part, take each part, the length of this each every part as h. So this one from this is h and this. So n equal parts, each part having h, having length h. Therefore, this BD, we have divided this distance into n equal parts, and each part we have taken the length as h. Now we know that this BD this whole distance B D. It is equal to the distance from the origin O D, and we will subtract it from this distance OD, this distance OB. When we will subtract it from this OD, this OB, we will get the distance that is BD. So therefore this BD is equal to OD minus this OB, which implies, but this distance BD, we have divided this distance into n equal parts, and each part we have taken distance as h. So if this is h, this is h, this is h, so on, this is h, and we have this h, if we will find out the distance BD, that is h plus h plus h plus how many times? N times. So it is this whole, the distance BD will be equal to now n h. So this BD we will write n h is equal to OD. What is that? That is equal to this x is equal to b, because we have from this O to D the distance that is equal to b unit. So I will write this b minus OB. What is the distance from this origin to this b? That is x is equal to a, that is a. So you take it as first. What we got? We got the distance BD is b minus a. Now after that, you draw AK1 perpendicular to this P1 B1, and this P1 K2 perpendicular to this, and then you take this P K and minus 1, the perpendicular. Now you have to draw perpendiculars from this point A to this P1 B1 and this so on, and after that you have to again draw perpendicular from this point to the extended portion of this B. For example, I will take that L, and from this point to this I will take it as L1, so on from here to this point I will take that Ln minus 1. So now I must have your pardon if you are not getting this the clear picture of this graph, but you have to remember it as this. We are taking first to the curve, and then we are dividing this distance into n, and then we are drawing perpendiculars to the line segments from the points that are on this curve to the line segment that is inside the curve, and after that we are again drawing perpendiculars from the point to the extended portion of the line segment. So here now this is my point A, and we know that the distance from the origin to this point B, that is x, that is x is equal to A, and then this point there must be the abscissa equals to A, and this point P we have from the origin distance to this B1, that is A plus this distance, that is h, A plus h. So this P1 has ordinate what? Equal to A plus h. P2 has ordinate equal to A plus 2h, and so on. So now abscissa of A1, A, P1, so on up to Pn minus 1 and C are respectively what beta? First one, A1 has abscissa as the distance, that is x is equal to A, that will be A, and this P1 has abscissa that is equal to A plus h, so on. This Pn minus 1, this one has abscissa, what is that equal to beta? A plus n minus 1 this one has this point C, it has B, it has distance equal to B. Now this point, that is, yes beta, that this point B, and that is equal to beta A plus N H. So here it will be A minus N. So this point, this might must have distance A minus A plus N minus 1 H. These are my ordinates. Now these are my abscissa of these, and ordinates of A so on up to this C are what beta? This we know that ordinate denotes the point that is on this y-axis, and we know that on this y-axis the points are the values of the function, that is f of x. So if this is the abscissa of A is A, then the ordinate of this A is f of A. This one has f of A plus h. So on the last one has f of A plus n h. These are my ordinates and abscissa. Now you write down this fast. I don't think you will get this graph. I will take this big. So here I will post it, because you will not get this graph clearly. So I will take it as, first I have a curve, that is this, and then I have this x is equal to A, and this x is equal to B. After that, I am dividing this distance into n equal parts. So I will take here B1, this B2, B2 up, so on this one Bn, and after that I am taking this, and we know that the distance of each, we are taking that h, then like this, and this is my A, this is my C, and this one I am taking as P A1 or P1. This one I am taking as P2, so on this one is Pk minus n minus 1. So here, after that I am drawing perpendiculars on this, and I am writing that's K1, this perpendicular. So I will draw here perpendicular, this one will be no. So from this point to this, so P2 here, so I am taking that K2, and so on from this point to this, I am taking that Kn minus 1. Now again I am taking perpendiculars from this point P1 to the extended portion of this A. Again, that is, I am taking K, that is L, and from this point I am taking to the extended portion this perpendicular. Again, this is L1, and then I am taking from this point the, again, this is Ln minus 1. This thing I am doing now. You check here beta. Again, now, again, this area of these rectangles, this A, B, B1, K1, these rectangles, the area of the rectangles that are inside this region, or that are between the curve AC and this BD, and this is DC, and this. So the area of the rectangle and this curve, that is beta clearly the area of this one, but it is less than beta the area that is under this curve and this thing, but that is also less than the area of the rectangle is this extended L B B1 L1. So this one, these are the, so I can say now here again area of this A B D C, area of A B D C, you write like this, area of this AK1, again area of AKB1B A B B1 K1 plus the area of this rectangle, that is area of what, this one, that is here P1 K2 B2 B1 P1 K2 B1, this what is here, yes, P1 K2 B2 B2 B1 plus so on, plus after the area this one, this Pn minus 1, area of Pn minus 1 Bn D, and then this one is K n minus 1 is equal to, I will take it equal to, now you check first area of A B B1 K, that is this rectangle. We know that the area of rectangle is length is breadth. What is the length of this rectangle? This A K1 B1 B, that is H. So it will be H into breadth. What is the breadth? Breadth is here. What is that, beta? This is and breadth is from this point A B. What is that equal to? This, that is equal to beta. That's of this A. The ordinate of this A, that is f of A, plus the area of this rectangle. What is that? Again, this time that is H, and then the length breadth, that is the ordinate this, that is f of A plus H, so on, plus area of this rectangle, this one, that is again length or breadth, that is length is H, and breadth is here f of this ordinate. What is the ordinate here? That is A, f of A plus n minus 1 H. So this is my area of this. So you take it equal to S, small s. This is your first area. The area of the rectangles that are inside the region A, C, B, D. I have taken that equal to S, and that is equal to this one. Now, also area, now I will take the areas of the rectangle that are extended to this L1, L1 to up to this. So I will take the area now rectangle that, the area of this A, this L1, this area L P1, this one P1, and then B1 plus area of this rectangle, that is area of this L1 P2 B2 B1 plus so on, plus the last, that is this one, that is area of L n minus 1 C, this rectangle L n minus 1 C D and B n minus 1, this rectangle is equal to, I will take it as capital S, and that will be equal to, now you check here, I have pushed a rectangle that is LP1, LP1, this one, B1, B. We know that its area is length is breadth, but length we know that is equal to H. What is breadth of this rectangle? That is this one. What is that equal to? That is equal to beta, the ordinate of this point now, L1. What is that? That is A plus H. So it will be f of A plus H plus area of this triangle, this rectangle, this one. That is breadth, length is breadth. Length we have H, and breadth we know at this point is f of A plus 2 H plus so on, plus up to this last one. What is that? Area of this rectangle. That is length is breadth. Length we have H. But what is the breadth here? Breadth is the ordinate of this point C. What is that? F of A plus f of A plus n H. So up here you take this second equation. Now clearly, as I have told you, the area of the rectangle, the sum of the areas of this rectangle that are inside this region A, C, B, D is less than the area that is under the square of AC and bounded by this AB, BD and BDC, just as we have done in the previous theorem. So I can say here, you write here, clearly this area of these two rectangles that we have taken as small s, clearly s small s is less than area less or equal to the area that is under the curve A, area of A, C, B, D, that is less or equal to the area that is the sum of the area of the extended these rectangles. So what is that equal to? That we have taken as capital S. This is my third equation. Now here you have to concentrate. You check here, I have taken a curve and then I divide this curve into n equal parts. Now this BD, I have divided this BD as into n equal parts. Now if I will tend this n to infinity, means if I will approach the n, if I will approach the number of parts of this BD into to infinity, that means the length between, when I will tend this n to infinity, the number of partitions I will make towards infinity, this distance it will get shrunken to 0, because when I have n parts the distance was h. But when I will take the more parts of this BD, I will divide it into more parts, or I will divide it into parts that are tending to infinity, then definitely this h will shrunken and it will approach to 0. So when I will, so it will approach to 0. So here you write as n tends to infinity, as n tends to infinity, h tends to 0. This h tends to 0. Now again, now limit h tends to 0 First you have this s equals to f of h f of a plus h f of a plus h plus so on h f of a plus n minus 1 h. This is my s, and this capital S I have equals to h f of a plus h plus so on plus h f of a plus n. This one. Now limit x tends to 0 s minus this s minus small s is equals to limit s tends to 0. Here you check, I have s minus s, that is this minus this. What is that equal to, beta? When I will subtract this s h f of a plus h, it will get cancelled to this, and this one will get cancelled to this. No, so this one will be here secure, and after that this one will also get cancelled with the term that is before this one. And what I will, when I will subtract these two, what I will get, s minus s I will get here. This is here, when I will subtract this one become minus h f of a, and plus the last term I will get h f of a plus n. These two terms I will get, and the rest will get cancelled. So here s minus s, that is this h of f of a plus h minus h f of a. These two terms are important. These are the important terms, but these are also complicated. You have to practice them at most 5 times, then you can get them, and they are very important also. So you have to take it in consideration. So here limit s tends to 0, this s minus s I am getting it equal to limit s tends to 0. What is h f of a plus h, that is limit s tends to 0 f of this h. I will take this h as common, because this is f of a plus h, f of a plus a n h, f of a plus n h. It is f of a plus n h. I have already given you in the first setup that this n h, that is this distance is bd, that is equal to b minus a. So I will write here b minus a minus f of a. So this one will get, a will get cancelled to a. I am getting here limit h tends to 0 h f of b minus f of a. So I am getting limit h tends to 0 h into this f of b minus f of a. What is f of b? That is the coordinate, this ordinate of the c, and minus I am getting ordinate this f of a. I know that it is the distance, actually this distance is, so from this point to this, so it is, when it is the distance, then clearly this distance c to a, then this distance from c to this point, and then clearly it is finite, because we are bounded to this interval bd, so it is finite distance, and we know that this limit can be obtained by giving the value of h directly. So when we will give the value of h directly, I will get 0 into this finite value, that is 0. Hence we got here, we are approached n to infinity, we get here limit h tends to 0, s minus s equals to 0. That means we got limit h tends to 0, this s is equal to limit h tends to 0, this s small s. So that means we got here we got now this s is equal to this s. But by the first condition, we have this small s less than this area less than this. So that means it is possible only when this limit turns to 0. So I will upload now in our condition, in our third condition, h to 0. So from third limit h turns to 0, the small s, you write this fourth equation, less or equal to limit h turns to 0, area of a, b, c, d, this is less or equal to limit h turns to 0, this s, and it is possible only when I have this area A, B, C, D, because in this area we have uploaded this n to infinity. Here the distance h turns to 0. So here this when I am taking this area A, B, C, D, limit h turns to 0, here is no h, so I can replace this h by nothing, by 1. So here it will be A, B, C, D is equal to limit h turns to 0 s, or it is equal to also limit h turns to 0 capital S. So I got here I got this area of A, B, D, C equals to area of A, B, C, D. But what is that equal to? That is integral of, by the area term, integral of A, B, f of x. This we know that it is equal to this. Now it is equal to limit h turns to 0 small s, and we got it also equal to limit h turns to 0 capital S. We know that this s small s, we have it equals to a f of a plus h f of a plus h f of a plus h, so on, h f of a plus n. Sorry, the phone got hang. Now we s is equal to the small s, we have it equal to this a f of this h f of a plus so on, h f of a plus n minus 1 h, and then this capital S we have equals to h f of a plus h plus so on plus h f of a minus a plus n h. So here I will put the values of this. So limit h turns to 0 s. So instead of s I will write here now h f of a plus h f of a plus h plus so on plus last one h f of a plus n minus 1 h. Second one I have capital S, and I will get it equal to also limit h turns to 0, and that is f of a plus h plus so on plus h f of a plus n h. So I am getting this integral now equals to, so limit h turns to 0, this thing is equal to limit h turns to 0, this one, it will be h is common everywhere, so I will take h here. So here it will be summation r is equal to 1 to n, because we are adding here the ordinates f of a plus h. We have this h we have already taken common, but we are not adding the ordinates. So it will be summation of f of a plus r, and you check beta to n yes, from r to 0 to n, r to 0 to n minus this n. You check here, when you will put value of r here, a 0, that will be f of a plus 0, that is this term, and then I will get by 1 this term, and after this I will get lastly this term. Similarly, this sum is equal to limit as tends to 0. This is 8, I will take it common, and then summation r is equal to 1 to n. This one is f of a plus r. How? Because when we will give the value first 1, I will get this term. When I will give the last value, that is this n, I will get a plus n. And this, no, n minus 1. This is my result bit. You will do it now. I hope you will fully make it in your mind, and you will try for it several times, so that you can get it completely, because this is a very important theorem we have proven here, we have proved. And the theorem that we have discussed yesterday, the ADA theorem, that is very important, and after that this is also very important. You have to keep them in your memory every time. So tomorrow we will find the application of these two theorems. It is other today.